Good morning. We were on the Lumina silica refractories, and we were part way through the phase diagrams. And this was the last slide from last week, and it's the alumina silica phase diagram with 100% alumina on the right and 100% silica on the left, and with one compound mullite. So we're looking at this phase diagram in detail, and just a little bit more on this phase diagram. This is in weight percent alumina, so you're looking about 72% alumina for mullite. And then this one is in mole percent, so it's 60 mole percent alumina in mullite. So what I want to do is just look at this region to the left of mullite from about 2.5 to 55 mole percent alumina and see how much liquid develops as soon as we cross this solidus curve of 1595 degrees, and that's degree C. So there's this phase field silicon liquid, and then this phase field mullite in liquid. So down at about 2.5, when we cross the solidus curve, as we increase the temperature, we'll have liquid and silica, and then above about, let's say 8 or 10% alumina, it'll be all mullite in liquid. So this is the plot of the amount of liquid as a function of temperature. So percent liquid from 0 to 100, and the temperature from 1550 to 1850 degrees C. And here's your solidus curve right here. So we're at temperatures above the eutectic. So at 55 mole percent alumina, and that's over here, close to mullite, you can see how little liquid develops, and then it starts to increase to 20% above 1800. But as we drop the alumina, here's 50 mole percent, there's more liquid present. 40 mole percent, the amount of liquid increases, and so on, 30, 20, and 10. So 30, 20, and 10. And you can see at the low alumina content, as soon as you hit the solidus curve, you're going to have a great deal of liquid present. And then this one here is 2.5% alumina. So this is the one that goes to silica in liquid. It's a little different, but still there's a lot of liquid present as soon as you cross the temperature of the solidus curve. So obviously the refractories that are 50, 55 mole percent alumina are going to be far better than the ones with the low alumina contents. And we talked about the Bayer process for making alumina, and there's some residual sodium in that process. And we mentioned this phase beta alumina, Na2O11, Al2O3. That's right here on this phase diagram. So this is 100% alumina, and this side of the phase diagram is NaAlO2. So beta alumina is right here. So if you're to the right of beta alumina in composition, this phase field is alpha alumina and beta alumina, and you don't see any liquid till 2000 degrees C. But if you're just to the left of this composition, here you have liquid and beta alumina, and that starts at 1580 degrees C. So sodium contents to the left of beta alumina are going to give low melting materials. Then I have a couple ternary phase diagrams: alumina, silica, and potassium oxide. So this side of the phase diagram, silica, alumina, is just the binary that we've been looking at in the compound mullite. And here's potassium. And what I wanted to show, here's the primary mullite field and the corundum field. But when you start adding potassium, there's various eutectics and peritectics and low melting compounds. So here's some temperatures, 1315, 1150, 1140, 985, 990, and some lower ones in here. So the addition of potassium to aluminosilica really lowers the use temperature. And then this is the one for sodium. And the same thing happens here. Here's your corundum and your mullite phase fields. And there's various eutectics and peritectics, 1062, 1050, 1104, 1063, 1270, and then some lower ones in here. So obviously these are not very useful refractories when you add Na2O. So what I thought I'd do on this same phase diagram, aluminosilica Na2O, is pick a fire clay refractory, 40% alumina, 60% silica, with a lower alumina refractory, and put it in contact with a slag composition, 80% silica and 20% Na2O, and show you how you can use a phase diagram to predict what will happen at high temperatures when you have this slag in contact with this refractory. So you can use the phase diagram. And these are really useful for corrosion studies. So the reaction products between that refractory and that slag composition are going to be located a lot along the line connecting the two compositions. And then the slag refractory interface, that is always going to move towards the direction of the slag composition, because the slag is going to be there in great excess. And as it dissolves the refractory, it's going to be moving towards the slag composition. So this red arrow just indicates we're moving from this composition, 40% alumina, 60% silica. As we dissolve the refractory, we're going to be moving towards this slag composition, 20% Na2O and 80% silica. So as we move along that red arrow, the first phase field we encounter is albite. That's the composition now in equilibrium with the refractory and the slag. Albite is Na2O, Al2O3, 6SiO2, and its melting point is 1104 degrees C. And here's your mullite phase field, your alumina or corundum phase field, and here's albite right here. And here's the melting point. 1104 is hidden sort of under the red line I put on that phase diagram, but it's right here. Here's the albite composition, and here's the albite phase field. So as soon as we cross into that phase field, we encounter pretty low melting composition of albite. So we connect mullite, silica, and albite in a compatibility triangle. Our initial composition is here. So when we cross this phase into this phase field, it's going to have to be mullite, silica, and albite. So now we're in this mullite, silica, albite triangle, and that has a low melting eutectic, 50 degrees C. So in this triangle, we're here at 1050. That's the eutectic for albite. So it's a little bit lower temperature. And then we're going to cross into another compatibility triangle. Sodium silicate is the next composition in equilibrium with the refractory and the slag. And that one is melting even lower, 874 degrees C. So this is the silica albite, and then the sodium silicate is Na2O2 SiO2. That's the compatibility triangle. And the melting point of the sodium silicate is 874 degrees C. That's composition is right there. And then finally, in this compatibility triangle, sodium silicate, silica albite, there's another eutectic at 740 degrees C, and that's right here, 740. So you can see the progression of the composition and how the melting temperatures change for that material. So this is a real simple example, but this is what you want to do if you're doing studies on potential corrosion issues. You can get your composition of the refractory, your composition of the slag, and see what happens as the composition changes. And this is really simple diagram, a two-component refractory, a two-component slag. And I mentioned that you can buy programs. There's probably about a half a dozen programs that have all the thermodynamic data for slags, glasses, refractories, and ceramics. And you can do the calculations for much more complex systems. You can include all the impurities, and you put in the temperature and even the atmosphere if it's other than the normal atmosphere, 20% oxygen. And you can calculate all the different phases that are going to be there and see what their melting temperatures are. And you can predict what's going to happen in terms of corrosion. I don't have any of these programs, but I can email everyone the list. I have a list of them, and I can email you what they are. Some are more for metals, some are more for ceramics. So I can send you that, and you can see what they are. They're all relatively expensive. They're roughly $30,000 a year, and I think there's about a $5,000 a year maintenance fee for all the upgrades. So that's what I have on the phase diagrams, and then how you make these materials. All the alumina silicate refractories are produced from uh, natural, raw, or synthetic materials. We talked about clays like kaolinite. It can either be a raw clay or it can be heat treated or calcined to control the shrinkage. Could be an anhydrous aluminosilicate like sillimanite, kyanite, or andalusite. Could be a synthetic mullite, which is can be calcined, could be fused. And then the bauxites, the hydrous alumina minerals like boehmite, dispore, gibbsite, they're synthetic also. They can be very fine particle size and reactive. They can be sintered to a high temperature and tabular, or they can be melted and recrystallized in terms of a fused grain. So those are the raw materials. All the processing steps for these materials are going to be basically the same. There's going to be some grinding step to get the right particle sizes. They're going to be graded into narrow particle size distributions. They're going to be blended back together, usually for maximum particle packing, minimum porosity, maximum density. There's usually a pressing operation or perhaps an extrusion operation for shaping, and then they're all fired and sintered. So general processing steps, this material is pre-fired or calcined, usually a clay, they call it grog. So the raw materials are pelletized, they're calcined, which is a sintering process, and then they're crushed into the right particle size distribution. So materials are usually calcined at 1500 degrees C. That gives the material dimensional stability. You remove water hydration, any other changes that might occur as a result of decomposition reactions or transformations. Then you sinter it and you densify it. So these are calcined, and they're known as grogs. If it's a clay, they're dimensionally stable, and then they can be mixed with other clays to provide plasticity. And these materials are mostly pressed. If it's a high clay content, it may be extruded for a low alumina type refractory. So the fire clay refractories are less than 50% alumina. You're going to start out with a calcined clay and a raw clay combination. And all of these are going to have the same steps. The materials are crushed, screened into various size distributions, and their sizes are put back together in a mixing operation to maximize density and maximize particle packing. And in the case of fire clay refractories, they can be dry pressed if the water content in that case will be 5 to 8% water. They could be extruded. You're going to have a higher water content, 10 to 15%. They go through a drying step to remove the physically held water, and they're fired. And these are not particularly high temperatures, 1100 to 1500 degrees C for these low alumina materials. So you're going to end up with some mullite, some cristobalite, probably some residual quartz, and a good amount of glassy phase. And there's a couple flow diagrams I have here. And this one is for dry pressing. And you might have your calcined clays here, grog. Maybe there's some flint clays, which are not very plastic. And then your plastic clays. And they're all going to go through this crushing operation and separating into the sizes. And here's another crushing operation. And they're going to go into bins, and then they're going to be mixed in the right proportion in a mixer. The amount of water for dry pressing is added here. The dry press dried, they're fired. And there's an inspection. If they're rejected, they go back and they're crushed into grog again. Basically, they're the pre-fired raw material. And the other one is just extrusion. Again, the same kind of raw materials, the same kind of crushing and screening and proportioning operations. And they may go into a pug mill or a wet pan, which are two pieces of equipment that are the raw material is mixed with water, and you have a plastic mass. That plastic mass goes into an auger, and there may be an additional sizing step. If the extrusion, the material that's extruded may be not very dimensionally stable, so you can go through a repress operation, and then it's dried and fired, and again, it's inspected, and the rejects go back into the process. When you get over 50% alumina, you're in the high alumina refractories, so 50 to 60% alumina. Now you're going to have a calcined anhydrous aluminosilicate like sillimanite or kyanite, Al2O3 SiO2, and maybe a raw anhydrous aluminosilicate like kyanite. Again, the same type of operations, crushing, screening, and mixing. At this point, you may even add a raw clay for plasticity. It's dry pressed, dried and fired, and the temperatures are getting a little bit higher, 1200 to 1600 degrees C for firing. And you should end up with mullite, cristobalite, and glass, those three phases. Then when you go up to as high as 80% alumina, you're going to have a synthetic material mullite, and another one alumina. So these are much higher alumina contents. And you probably have a small amount of a raw clay present. Again, it's crushing, screening, and mixing, followed by dry pressing, and that's always a low water content. Drying and then firing. So the firing temperature is going up with the alumina content, maybe 1500 to 1700 degrees C. Now you should end up with a great deal of mullite, because mullite is about 70% alumina, some corundum, and then the amount of glass should be a lot less. So the glass phase will be minor in this case. And then refractories that are up to 90% alumina, you're going to start out with the calcined bauxite. So it's calcined alumina. Again, crushing, screening, and mixing. A raw clay, a small amount of a raw clay may be added for plasticity, then dry press, drying, firing. And in this range, 1500 to 1700 degrees C. Again, it's going to be mullite. Now, there's going to be a little bit more corundum present because of the higher alumina content, and the glassy phase should be pretty minor. And then the ones with the highest alumina contents, much greater than 90% alumina, it's going to be either calcined or a sintered tabular alumina or a fused cast alumina. Same sizing and mixing operations, maybe a raw clay addition for plasticity, dry pressing, drying to remove the water, and then firing is going to be much higher temperatures, maybe 1800 to 1900 degrees C. And again, it's mullite, and now there's going to be more corundum because of the high alumina content and a very small amount of glass. So that's how they're processed. They're all following the same type of operations. So a couple generalizations about the microstructures and the properties. So at room temperature, for the microstructure, it's going to be crystalline particles bonded by either smaller crystalline particles. And when you have crystalline particles in contact with other crystalline particles, that's known as direct bonding. Direct bonding tends to give you better high temperature properties, like high temperature strength, or you may have a glassy bond and you're going to have porosity. Then you go up to the use temperature, a high temperature, you're going to have a liquid phase that develops. So the crystalline particles are going to be bonded more by a molten glass. And for the properties at room temperature, the properties are going to be determined by the amount and type of crystalline particles, glass, and porosity. There's a third course in this sequence on properties, and then we look at all of these factors, how it affects creep resistance, how it affects strength. But these materials tend to be pretty strong at room temperature because they tend to be bonded by a glass phase, and which makes it relatively strong at room temperature, more of a brittle material. But then when you go to high temperature, that glass softens. So the high temperature properties are going to be determined by the amount of the liquid phase present and its viscosity. So a more viscous phase is going to be a better material. So if you have less than 50% alumina, some generalizations about the microstructure. At room temperature, you're going to have mullite and cristobalite, and it's going to be bonded most likely by a glass. The mullite forms needle-like crystals, and they tend to interlock, which gives rise to some good high temperature properties. And then at high temperature, you're going to still have mullite and cristobalite and your viscous glass phase. And the higher alumina materials, 50% or higher alumina, at room temperature, you can have corundum, which is alpha alumina, mullite, cristobalite, and some glass present. And again, the mullite's going to form needle-like structures. And then finally, at the highest temperatures, you're still going to have corundum and mullite and cristobalite, but now the glass is going to be a viscous glass. probably much more viscous than in the case for the lower alumina refractories. So the fire clays that are less than 50% alumina are mixtures of medium and coarse clay grogs with the raw clay binder. The ball clays, which are the very fine particle size clays, are added to increase the plasticity, but they also have more impurities present, so they also increase the impurity content. Then you can also add some bauxite if you want to improve the alumina content. So bauxite is a much higher alumina content than the clays. There's a densification process, and again, there's another course that we have in this sequence that's all on densification and sintering. So the densification during firing occurs by a liquid phase sintering process, and you're going to have an aluminosilicate liquid. So it's going to be a silicate-based glass or liquid. This glassy aluminosilicate matrix becomes solid at room temperature, and it's going to bond the aggregates, which are the pre-fired clays. And as it crystallizes on cooling, this glassy aluminosilicate matrix, the bonding phase, it's going to develop crystals of mullite. So the softening temperature, viscosity, and distribution of this glass phase, that's the matrix, is going to affect the high temperature strength and creep behavior. And same materials, these low alumina fire clays. Mullite forms, again, an interlocking needle-like structure. Those interlocking needles give rise to high strength and good creep deformation resistance. And then this mullite content in the matrix is going to increase as you increase the alumina content. And one thing about these fire clay refractories, there's thermal expansion mismatches. So cracks can also develop around the medium and coarse aggregates, not only due to thermal expansion mismatches, but due to shrinkage of the matrix. The matrix would, be a raw clay, which would shrink away from the pre-fired aggregates. So this is an example of a microstructure. The dark black areas are porosity. This is a large aggregate or grog. You can see another one over here. And then the matrix, the bonding phase is between these medium and coarser aggregates. And then here's an example of the matrix shrinking away from this coarse aggregate. So here's a crack that forms. And then in these polished sections, it looks like something's there in that crack. Well, there is. It's usually the resin that's used to make the polished section. So you can see another crack here filled with resin and another one here. So here's an example that I looked at. This is 20X for a low alumina fire clay. It's 45% alumina and 52% silica, and there's some titanium, iron oxide, and potassium oxide present. And the black is porosity, and you can see some cracks that are forming. You can also see the at this magnification a coarse aggregate. Here's another one over here. There's another one over here. In between these aggregates are this very fine matrix. So the matrix is clay-based. The aggregates are clay-based. They're going to have the same composition. It's not easy to distinguish them with like EDS for mapping. They're all the same composition. But here's a 500x magnification of a boundary. The boundary here between the porous matrix. So all these little circles are basically pores, and a denser pre-fired aggregate. So here's a pour that's filled with resin. And you can see this is about 44% alumina. This is 45%. This is 49% silica. This is 51. So this is the sintered matrix. This is the pre-fired coarse aggregate. And basically they're the same composition. And then looking in that matrix at 3500X, much higher magnification, you can see all these needle-shaped crystals. Well, they're mullite. So an EDS analysis over here is about 64% alumina and 32% silica. And the one thing about EDS analysis, it covers an area, so it's probably picking up some silica in this darker phase, which is the glassy phase, which is about 64% silica and 28% alumina. So you have these mullite crystals, the lighter phase, needle-shaped crystals, in a glassy matrix. The materials that are 50 to 60% alumina, there are several ways to make these. You have a variety of raw materials. You have bauxitic clays, which are natural mixtures of bauxite and clay. So it's clay enriched with bauxite. You have diluted bauxite. So your bauxite that's been calcined plus a clay. And then you have your anhydrous aluminosilicates like kyanite, andalusite, and sillimanite. So you have all different combinations of these raw materials now when you get up to the higher alumina contents. So we looked at the phase diagrams, and the high alumina refractories start melting at the same temperatures as the fire clay refractories. They have the same solidus temperature, but they have higher refractoriness because less liquid develops. So the amount of liquid that appears at the eutectic temperature is less than the fire clays, and the amount of liquid slowly increases as you increase the temperature above the solidus curve. And these materials have more mullite present, so it's a greater quantity of these interlocked needle-type crystals. They're still in a glassy matrix. So you have increased amounts of solid contact with this mullite formation, and that's direct bonding, and direct bonding tends to isolate the liquid. And when you have direct bonding, you're going to have better high temperature properties. So here's a sample microstructure at 60% alumina. You can see a sintered alumina, high alumina particle right here. The black is the porosity. So this is an aggregate. Here's another one. Here's another one. And the bonding phase, there's a lot of smaller, finer particles of the calcined aggregates, but in between there's a matrix in this little bit darker gray region. So when you get up to maybe 75% alumina, you're starting to use these mullite aggregates, whether it's a sintered or a fused material. Again, the sintered is just a mixture of kaolinite with alumina. Could be bauxite, calcined alumina, tabular alumina, or a fused mullite, which is a mixture of calcined alumina and high purity silica. And then we mentioned in this fusion process, a lot of the impurities will vaporize, especially the alkali, and increase the impurity of the fused material. And then materials up to 90% and even greater than 90% alumina, you're still going to have aluminum, mullite, and glass. So 80, 90% Al2O3, calcined bauxites, and a minor amount of clay. You're going to have aluminum, mullite, and glass. And then higher alumina refractories greater than 90%. You're probably going to start out with tabular aluminas, maybe a fused alumina, minor amount of clay. So now you're going to have alumina and glass. you're going to probably have a little bit of mullite, but when you're up in 90% alumina, it's going to be mostly corundum. So here's another one I looked at greater than 90% alumina. It's actually 91% alumina and about 8% silica. There's some residual sodium that was picked up here. Here's a coarse aggregate of alumina. This aggregate is about 97% alumina and 3% silica. The black is the porosity. And then you can see the bonding matrix, which is about 85% alumina and 14% silica. So the bonding matrix is going to be high mullite content and some corundum. So the green is mapping for aluminum. So the brightest green, you can see the coarser aggregate here. You can see some medium aggregates and even some fine aggregates. And then the darker, less bright green is going to be the bonding matrix, lower alumina content. And if you map silicon in blue, you can clearly see where the bonding matrix is. So that corresponds to this darker green region. So the alumina and silica are in the bonding matrix. Shows up rather clearly there in blue. And then if you go to a higher magnification, 1000x, you can see this coarse aggregate, and basically this one comes up by about 100% alumina. It's pretty large crystals. It looks like it's probably a tabular alumina to me, and the matrix was designed to be mullite. This particular matrix region right here is about 61% alumina and 35% silica. And here's where your impurities are concentrated. An alkali, sodium oxide, another alkali, potassium oxide, and some MgO and CaO. But even at this magnification, you can start to see the brighter phase in the matrix. That's the mullite, the needle-shaped mullite crystals, and a little bit darker gray glassy matrix. So if we look at some of the properties, this is a less than 50% alumina fire clay. So this is what happens when you heat it up in terms of thermal expansion. So this is 0 to plus 4%, and this is 0 to minus 2%. So this is expansion, and this is shrinkage. So we go from A to B. So the thermal expansion, starting out with the raw clay, A to B, is reversible. So you can heat this up to about this temperature and bring it back down. And the curve should repeat itself, the heating and cooling curves. So it's reversible. But then when you get to temperatures higher than this point B, you have irreversible shrinkage. You have the sintering process, the densification process taking place. So here it starts to sinter and densify and shrink. So you get to some temperature here. This is about 1200 degrees C. That's about where mullite starts to form. So from C to D, you have, again, irreversible expansion. That's actually irreversible shrinkage due to mullite formation and glass evolution. I'm sorry, it is irreversible expansion. The sintering is irreversible shrinkage. So C to D, mullite forms, and again, mullite's a lower density phase, so there's a substantial volume increase or expansion. Also from C to D, clays contain sulfur, so you might form SO2 gas that comes off. They contain organics, which are carbon sources, so maybe CO2 might come off, and they're hydrated, so water will also come off. So any of these may cause expansion. So you can see if you design the microstructure properly, you can have this expansion from C to D taking place, and you can have it take place in service. So if you're trying to avoid a mortar between the bricks, that expansion basically closes the joints. So you can design that into a lining. Obviously, when you close joints, you prevent slag or metal penetration. And then D to E is more irreversible shrinkage. That's where your glass is forming and your material is starting to deform and shrink. So that's what happens when you heat up a fire clay. So the high temperature strength, the creep resistance, uh, at high temperature, you have a strength loss and you have creep deformation because of the glass that forms. And you can see that readily right here on a thermal expansion trace. You can see where the glass forms. Anytime you have impurities, the sodium and potassium alkalis or an iron oxide, that lowers the melting or softening temperature of the glass matrix. And the alumina content, the melting temperatures are going to go the other way as you increase the alumina content. We can see that from the phase diagrams. The more alumina present, the more mullite, the less glass. And again, the nature of the mullite crystals are providing these needle-like structures that give rise to good high temperature properties. 50 to 60% alumina, you're using sillimanite, kyanite, or andalusite, and you can have this irreversible expansion when you convert to the lower density mullite at high temperature. So when any one of these anhydrous aluminosilicates convert to mullite, you have this volume expansion. Because of the presence of mullite, mullite's low expansion, it's going to be not only good in terms of creep resistance and hot strength, but the low expansion is going to give rise to thermal shock resistance. So these materials, 65, 75% alumina, are going to be synthetic mullite. And I mentioned thermal shock resistance. Mullite has a thermal expansion coefficient of 5.3 times 10 to the minus 6 per degree C. The centimeters cancel. Alumina is about 8.5 times 10 to the minus 6, and MgO is about 13.5 times 10 to the minus 6. So you can see one of the advantages of a mullite-based material, the lower thermal expansion is going to give good thermal shock resistance. And again, the nature of the microstructure with the needle-like crystals, good hot strength and good creep resistance. So mullite is a pretty good high temperature strength material with pretty good thermal shock resistance due to low thermal expansion. And then when you go up to these higher alumina based materials, 80 to 90 and greater than 99% alumina, that's synthetic corundum. And now the thermal shock resistance is going to go the other way as you increase the alumina content. You're going to have more corundum and less mullite present. And alumina has a thermal expansion coefficient of 8.5 times 10 to the minus 6 per degree C. So the higher thermal expansion is going to decrease thermal shock resistance. But the higher alumina content, it's going to be alpha alumina, is going to improve the creep deformation. It's going to improve the high temperature strength. It's going to improve corrosion and abrasion resistance. It's a very hard material. But you're going to lose thermal shock resistance. So these fire clays and high alumina refractories are classified based on their softening temperatures. And that's basically the upper use limit. You don't want to necessarily go to the softening temperature. You want to be a few hundred degrees below that. And they're classified by PCE or pyrometric cone equivalents, and that's an ASTM standard C27. So the higher the PCE number, the higher the use temperature. So a low duty fire clay, it's only a 15 for PCE, maybe 15 to 27. And then the range, 15 to 27 PCE value is 1430 to 1640. And then a higher aluminum material would be a 36, and that temperature range is 1820 to 1850. That would be a 37 to 38 cone. So this PCE test, you take your raw material or a refractory material and you press it into a small cone. These are only about an inch tall and a quarter inch across the bottom. It's this pyramid shape, and it's pressed so that the base is at an angle. And this is 8 degrees here. This is 82 degrees here. And these cones are placed into a cone plaque of some type, and this one happens to be a circular one. So you put in standard cones. So there's a set of cones that are standardized. This one goes from 20 to 29 to 30, and back up here 31 up to 42. And these are different chemical compositions that have endpoints or softening points at these temperatures. So these are your known standards. So a cone 12 would deform at 1337 degrees C and a cone 40 at 1885 degrees C. So when these cones deform, the endpoints I just showed you is when the cone touches the plaque. So they bend over and touch. That corresponds to one of these temperatures. These are pretty accurate within plus or minus 2 degrees. So you put your known standards, and these are numbered here, 20, 23, 26, and so on. And then in between the standards, you have your unknowns. And you simply, when your unknown bends over and touches the base here, you look and see which standard cone corresponds to that one. So you have to watch. Usually it's best to watch these. And usually this cone plaque is rotating in a furnace. So those are what the PCE test looks like, and that's how they rank these materials, especially useful for the fire clay materials. So a super duty, it usually has to be a 34 or higher to be ranked as a super duty. So I just have some properties here. These are actual items from data sheets. The high duty, super duty, and super duty. So different fire clay-based refractories. The bulk density is always in pounds per cubic foot. They're around in the 130s up to 140. You can see the porosity levels, 15 to 20%. That's pretty typical. A cold MOR is a bend strength. And then the cold crushing is a compressive strength. Typically, refractories are always, and ceramics are going to be stronger in compression than in tension, usually 5 to 10 times stronger. So these are less than 2,000 in cold MR. These are 3 to 8,000 in compressive strength. And those are in PSI. And this test is pretty useful. It's kind of a creep test. It's called the hot load test. So you start out with a full-size refractory brick. You load it to 25 PSI, and then you hold it at these different temperatures for an hour and a half. And you simply measure the initial length, the final length, and get the percent deformation. So hot load is the percent deformation, and usually you want less than 2 or 3%. So this high duty is tested at 2460 degrees F, and then you go up to Super Duty, they're tested at a little higher temperature, 2640 degrees F. So this one is a little bit high in this deformation. So this high duty is about 36% alumina, and the Super Duties are a little more than 40% alumina, and then the balance would be silica and Fe2O3, TiO2, and the alkali oxides are your basic impurities. So as we go up in higher alumina content, the densities go up over 150. These are about 15% porosity. They tend to get a little stronger. So the bend strengths are around 2,000 and the crushing strength are around 7,000 PSI. This one was tested at 2460. This one was tested at 2640 for the hot loads. Pretty low deformations on these materials. And then the alumina content should correspond to this class of refractory. So this is 50% alumina. It's got 50% alumina. This is a 60% alumina. In the industry, it's always a little generous, usually plus or minus 2% or more. So a 58% alumina is really a 60% alumina refractory. So the balance other than alumina is mostly silica, and then your typical impurities. So 70, 80, and 90% aluminas. The bulk densities are going up from maybe 150 range to almost 190. The porosity, 13 to 20%. It's just a function of how the material was pressed, the particle size distribution, and the firing temperature. But these are typical porosities up to 20%. The cold MOR, some of these are having a little bit better, especially this one with the low porosity. And then the crushing strengths are going up 8, and this 8,000 all the way up to over 20,000. So these higher strengths on the 90% alumina are due to the low porosity and high alumina content. So the hot load test, you can see the temperatures are going up here. This is 2910. This one was lower, 2640, another 2910. And this one was all the way up to 3100. So these are all pretty low deformations, 2% here and 0.5% here. So this is these first two are 70% alumina. This one is 80, so it's 81%. And this one is 90, it's 90%. So your alumina contents, the balance is silica, and then your impurities. And as you get up to the higher alumina contents, you can see the impurity levels are dropping off dramatically. And then I think this is the last slide, some higher alumina contents. This is 97.5. This is almost 100%, 99.6. The density here is almost 190. This one's almost 200 pounds per cubic foot, 20 and about 16% porosity. And the cold MOR is a little bit higher here. This one's over 3,000. This one's almost 3,000 PSI. I just mentioned the alumina contents. And then you can see, especially on this one, a lot of these impurities are a trace. So there's going to be basically alumina crystals, a lot of direct bonding. And either one of these, this one will have a little bit more glassy phase present in the grain boundaries. So that's some examples of some properties, some basic properties of these different aluminas and alumina silicas. So I'm going to stop there. And next Wednesday, we're going to start basic refractories, and that'll take another 2 lectures. So we'll start with the MgO materials, the dolomite, the MgO chromes, phosphorite, and some other materials like spinel. So we'll take the next 2 lectures and go over the basic refractories. Ken, if you have any questions, you can always interrupt or please send me an email. Otherwise, have a good rest of your day and I'll see you on Wednesday. Again, thanks for listening in.